All right, let's talk about implicit differentiation. This will be a fairly quick video. The idea is fairly straightforward, although actually solving problems with it can be challenging. But the idea is pretty simple. And so let's set up why you would do implicit differentiation and what it is. Sometimes it's challenging or inconvenient to solve an equation for just one variable. And when that's the case, rather than solving for the y of x, you can differentiate the whole equation. This is like thinking about the derivative as an operation that you do on the whole equation, and then you can use algebra to solve for what the derivative is that you're looking for. This process is called implicit differentiation. You're not solving for y of x at the start and then differentiating y. You're differentiating the whole equation, and then that implies that you will have the derivative of y in there that you can then solve for. So I'm not sure how clear that is, but let's think about this particular example right here. You have x squared plus y squared equals 25. One option would be to solve for y, and then you have y as a function of x, and you could probably do this in your head maybe. So you have 25 minus x squared, square root the whole thing. Then you have to worry about whether it's plus or minus. This is the formula for a circle of radius 5, by the way. So one way would be to solve for y, and then you could just take the derivative of y using the various techniques that we've talked about before. An alternative approach is to say, let's not bother with that. We can differentiate this whole equation. So do d by dx of each term within, and then in the process, and using the chain rule, we'll have the derivative of y in there somewhere that we can then solve for. The textbook explanation of this process, I think, is correct, but it's a little bit laborious and makes it seem more difficult than I think it really is. I like to think of this as just you're taking the derivative of the equation, and then you need to know what that means. Let's try an example, and I think it'll be a little more clear. So we have our x squared plus y squared equals 25. That is this circle right here, a circle of radius 5. And let's suppose we wanted to know the slope at any point along the circle. Well, implicit differentiation means taking the derivative of the whole equation. Now this works because anything you do to the left side, you do to the right side. That's a legal mathematical operation. So if I wanted to divide everything by 10, I could divide everything by 10. You can also differentiate every term in the equation. And now that we know the chain rule, we know how to do that when we encounter functions that are, say, composite. And in this case, y is a composite, right? It's y of x. It's not just y. We want y of x. So we can take, sorry, I should say y squared is the composite function. It's not just y by itself. So as we go through, we're taking the derivative with respect to x of each term within. We get to x squared, that becomes 2x. We get to y squared, we use the chain rule. So it's 2 times y, then take the derivative of the inside, dy dx. So 2y dy dx, that's our chain rule. And then derivative of 25, that's a constant. Constants always give you 0 when you differentiate them. Okay, so by differentiating the whole equation, i.e. using implicit differentiation, we now have an expression that involves the derivative of y. And then it's just algebra, solve for this unknown variable, and the unknown variable is the derivative of y. So subtract x from both sides, subtract 2x from both sides, divide by 2y, and you'll get minus x over y. And so now we have a neat expression for the derivative, and we never solved for y, we just solved for the derivative after implicitly differentiating the equation. And so if I pick any particular values of x and y, I can find its derivative. So let's say I picked, like, I don't know, what's this, minus 4 and plus 4, or maybe it's minus 3.5. It's hard to tell. And plus 3.5. You'd plug that in here, minus 3.5 divided by plus 3.5, and there's an overall minus sign. It just gives you 1, and so we get a line with a slope of 1. All right. So this is an example of implicit differentiation. This is always an option when you have an equation written like this, where it's not solved for one particular variable. You might just try differentiating the whole equation and then solving for the derivative. Now, it could be easier the other way, but this is always an option. And a lot of what we're doing here at this stage of the course is learning what the options are for finding derivatives, and implicit differentiation is a particularly useful one.